Good morning. Can you hear me? Yes? Do I have to speak loudly, or can you hear me if I speak in a more subdued tone? No? I need to bump it up a little bit. Well, I'm probably going to speak like this, so that's fine? Okay. I'm going to crank it up just a little bit anyway. What the hell? Okay. So my name is Lenny Pitt. As you might have recognized, I'm not Chandra. Chandra is traveling, and so he asked me to fill in today. And I'm delighted to do so because, first of all, you're all relieved because the exam's over. And second, I think the material that is covered today is some of the most beautiful material in computer science. It's just really, and it's a little bit mind-bending. So it's really a lot of fun, but it can be confusing. So we're going to go slow. We're going to take you through a bunch of interesting bits. So first we need to recap, I hope, what is a recap of Turing machines. So if you remember, a Turing machine is basically a finite state machine, a DFA, which also can write. So you can go back and forth on this tape. It can write, it can read, and so on. What were the high-level points that hopefully you've already learned? The Church-Turing thesis, which is that a Turing machine, this very simple device, is as powerful as any computer in terms of what it can do, not necessarily the speed, but is as powerful as any computer that anyone has been able to imagine or design. And in fact, and it can simulate real-world computers, even with only a polynomial time slowdown. So, I mean, it's very cumbersome going back and forth, but nonetheless, it can do anything that we have imagined that could be algorithmic. So it captures our intuitive notion of algorithm. Every Turing machine can be represented as a string. It's just a program, a sequence of characters. We'll take a look at that in a moment just to remind you. And then finally, there is a universal Turing machine, which is perhaps more surprising. And I know you've seen this. There's one Turing machine. There's one simple device which can take as input the description of another device, the code for another Turing machine, and an input to that other Turing machine, and simulate it and do what it does. Right? So we don't need a different Turing machine for each task. We've got one. We can build it and park it here or at Siebel, and if we want to program something, we just give it the code, which is the description of another Turing machine, and the data, which is the data we want the universal Turing machine to run this described Turing machine on, and it can do it. So one universal Turing machine. Okay. So let's talk a little bit about decision problems. So these are yes-no questions which admit many instances, and they can correspond to languages in a way we'll see in a moment. But there's a lot of interesting decision problems we might want answered, as opposed to optimization problems or search problems, which you've been addressing in the algorithms part of the class. So, for example, given a grammar, is it ambiguous? Or given a Turing machine, is a language equal to every possible string? Given a graph, is it connected? Given a graph and a start and a finish node and a number d, is there path in the graph from the start to the finish of distance d or less? Right? So these are just very interesting questions. You can see they come up just about anywhere. Any search problem you might have, all the algorithms you've been designing can be rephrased as simple decision problems. And decision problems really correspond to languages. So any yes-no decision can be termed or can be phrased in terms of, is a string in a language or not? So for example, let's just look at, is a graph connected? We can consider a language which consists of graph descriptions that happen to be connected graphs. And whether or not this description of a graph is in that language is deciding whether or not the graph is connected. Right? Or similarly, given a graph and a string, and a start node and a finish node and a distance, look at strings that look like this, where the first part encodes a graph such that there's a path of length d or less from the S part to the T part, right? So that language consists of the graph problems that have yes answers. So deciding membership in these languages really corresponds to deciding the problem, deciding the yes-no problem. And so it's convenient to talk about languages because that's what we've been doing when we've talked about Turing machines or finite state machines. What languages do they accept? But I'm just pointing out that accepting a language is no different than making a decision, right? Okay. Good. I'll remind you of the definition of decidable. A language is decidable if there is a Turing machine, or a program, if you will, that can take a look at an instance of it, an input, a potential string in the language, and halt and say yes or no correctly. That's what it means to be decidable. So a yes-no question is decidable if there's an algorithm to always say yes or no correctly. Or a language is decidable if there's a Turing machine which always halts and accepts the language and says yes if the string is in the language, and says no if it's not. So none of this infinite looping or crashing or anything. Okay. Yes, question? No, so if it gives the wrong answer, then it's not decidable because it's deciding something else. Otherwise, sorry, so the question was, is a language decidable if there's a Turing machine which doesn't always give the correct answer, but nonetheless always halts, right? And so the answer is no, that's not what decidable means, because otherwise everything's decidable by the algorithm that simply says no. I always halt, I say no, right? So for the definition to make sense, we want a correct and halting algorithm to decide the problem. Otherwise, we're deciding some other problem. So things that don't work right aren't decidable. Okay. Okay, so let's give some examples which will get our heads around this idea of decidable. So consider the question, is there a string, or a substring rather, of exactly 374 sevens in the decimal expansion of pi? So is that decidable? So how many people think this is decidable? How many people think it's not decidable? Okay, and the answer is it's decidable because there is an algorithm that can tell us yes or no whether or not there is a sequence of exactly 374 sevens in pi. But let me show you the algorithm. Well, actually, I'm going to show you two algorithms, okay? I'm not quite sure which one is the right one, but here they are. So this algorithm here simply says yes. So yes, there are 370, there is a subsequence of 374 sevens in pi. This other algorithm says no. Now, one of these is correct, right? And they always halt. They don't even look at the darn input. So they correctly decide that question. All right, now you may take issue with the fact that we're not quite sure which one is the right algorithm, right? But in fact, I've got a way we can figure out which one is the correct algorithm. So do you want to see it? Okay, well, actually, I've got two ways. I'm not quite sure which is the right way. So here's an algorithm for deciding which one is correct. That one's correct. Okay. And then here's a different algorithm for deciding which one's correct. That other one's correct. One of those two algorithms is correctly giving the answer to which one of these is the correct algorithm for deciding this question. Okay, so what's going on? This is nonsense, right? And the point here is that a question, a single question, for which is a single yes-no answer, is not something we can model well with is there an algorithm for, right? We're interested in more general questions which have more general inputs, where there's a range of possible inputs, and we'd like to know for any given input, is the answer yes or no? So here we're asking about 374 sevens. It doesn't make sense to write an algorithm. Well, it might make sense to write an algorithm to try to figure out the answer to that question, but it is decidable, so our theory doesn't quite cover this kind of a question. On the other hand, here's a more interesting question. Given an input n, is there a substring of exactly n sevens in the decimal expansion of pi? That's a more general question. So now we have so now maybe there's an algorithm that will input n and do some computation and say yes or no and always halt and always be correct. So see the difference between the first question and this question. Okay. This question has an input n, and we need to answer that question regardless of what n is. The previous question, it was only a single question. It wasn't a collection of questions with an input n. We only wanted to know about one particular value, 374. So is this decidable? Notice that the previous trick isn't going to work here, because there may be some numbers for which there is a substring of exactly that many 7s in pi, and others for which there isn't. So sometimes the algorithm is going to say yes, and sometimes it's going to say no. And the question is there an algorithm that can do that for pi? So how many people think yes? How many people think no? How many people don't know? Okay, that's what my hand is. No idea. Okay, so I don't know if we know how to tell whether or not there's exactly a sequence of n 7s in pi. Okay. Okay. But there is, well, I guess it is recursively enumerable. What does that mean? It means there is an algorithm that will say yes if there is a sequence of n 7s in pi, but may not say no if there isn't. Right? Remember, that's what we call recursively enumerable. And the algorithm to do that would simply create the decimal expansion of pi using whatever summation or infinite series you'd like to more and more digits of precision, and then see if it ever came across exactly n 7s surrounded by non-7s. It would say, yes, look, found it. But otherwise, it may search forever. And we may not be able to tell if it was going to do that. So it's recursively enumerable. We have a way of saying yes. We don't know, I don't know, whether there's a way of saying no. And this problem of deciding whether or not an algorithm is eventually going to tell us an answer is related to a problem called the halting problem, which we will discuss shortly. Yes? Yes, actually, I want to even say something. I want to say that's not even a well-posed question, because what is the language associated with the question, are there 374 consecutive 7s in pi? What is the language associated with that? I don't even know how to phrase that as a language decision problem. Now, I know how to phrase, are there n consecutive 7s as a language decision problem. It's the set of n such that there are n consecutive 7s. I kind of headed your question off in a different direction, but I'm not sure if it answered what you were getting at. You're okay? Okay. All right. So let's take a look at a third example. This is related to the previous example. Is there a substring of at least n consecutive 7s in the decimal expansion of pi? So in other words, is the substring 7 to the n appearing in pi? Now, there need not be non-7s surrounding it. So it could appear in a longer string of 7s. Different question. So, decidable? Undecidable? Don't know, you've really confused me more for the day already, and I just had enough already, and yet it's only 10 minutes into the lecture? Okay, so yes, this is decidable. It's regular. What? What? All right, so I'll explain why. The moral is going to be, you need to be careful. Theorists have no end of tricks. So, look, are there arbitrarily long sequences of 7s in pi? Yes? Yes? No? I'm not even sure, but let's suppose the answer is yes. Then what is that language? If for any k, you can find a sequence of 7s which exceeds k, of length that exceeds k, in pi. Suppose that were true. What does that language turn out to be? It's everything, right? All numbers, right? So look at the number 57. Is that in the language? Well, if for any number like 57, there is a substring of length at least 57, then it should be in the language, right? And so if for every length there's a string at least that long or longer, if there's no bound on how long the longest sequence of sevens is in pi, if there is no bound, then this language consists of the natural numbers, which we can certainly accept with a finite state machine which has a single state which just accepts. Does that make sense? If for every n there's a substring of 7 to the n in pi, then that language is the set of all n, which is a regular language. But what if that weren't the case? What if, in fact, there's some number, 1,284, and that's it? You're not going to find a substring of 7s longer than 1,284 in pi. Then what does that language look like? It looks like the numbers up through 1,284. So the language is finite. Okay, so this isn't important. It won't be on the exam. It's just sort of a teaser. So let's go on and get more confused. So let me remind you of the universal Turing machine. Again, there's a single Turing machine which can take the description of another Turing machine, M, as input and data for it, and run M on the data and output the result. Everybody's comfortable with that, yes? Good. And another recap, here's what the code of a typical Turing machine looks like. It's a natural number written in binary. So, we've encoded, this says the beginning of the description of the Turing machine, that says the end. A pair of ones means the end of a transition description. A one separates fields in the transition. So this says if you're in state 1 and you're reading the character 1 and 1, 2, 3, 4, 5, you should go to state 5 and write whatever, 0, and move to the left, something like that, right? I don't remember exactly. But we have some clever way of writing down the description of a Turing machine so that it's a natural number. Okay, that's all you need to know. Okay. And finally, we saw that this language, description as a natural number of a machine, and input, such that M accepts W. We saw that this language is recursively numerable. That is, there is a Turing machine, the universal Turing machine, which takes a machine code, a machine description, and an input, and basically runs the machine on the input and says yes if it accepts. If it doesn't accept, it may not say yes. I mean, it can't say yes. It may say no. It may do something else for a long time. Okay? But nonetheless, we have such an algorithm, right? The universal Turing machine. It's really just a program. It's just a computer. Computer, you give a program and data, and you can ask if this computer is correct. You can ask, does this program run on this data? Does it end up saying yes when it does it end up accepting? So we know how to do that. Okay, we already went over those points. So here's where we're going today. We're going to talk about things that are not decidable. So here's this lovely hierarchy. If it was spinning, then you'd all be under my power. So at the very bottom, there are things that we can do in linear time and things we can do in n log n time, right? So this is larger and larger, harder and harder problems, right? Or easier and easier problems as we go down, right? Problems that don't take us as much time. Here's polynomial time. You probably haven't heard about non-deterministic polynomial time yet. Maybe you have. Things you can do in an exponential amount of time. the recursive languages, these are things that we have yes-no algorithms for, things that we can do. And then outside of that, are recursively enumerable, well, actually, including that are the recursively enumerable languages. These are problems, decision problems, or languages for which we have an algorithm that will say yes if it's in the language, but if the input is in the language, it may not say no, if not. And the languages outside of that big red circle are called undecidable. And languages outside of the blue circle are languages that are not even accepted by any Turing machine. They're not recursively enumerable. We don't even have an algorithm that can say yes when it should, let alone say no when it should. Okay? So we're going to see both kinds of languages today. Okay. Okay, so that's where we are. So I'm not sure if you've seen this counting argument before. You may have. This is the argument that not every language has a Turing machine. And the reason is that there are far more languages than there are Turing machines to go around. It's a very simple counting argument. Basically, it's a difference between uncountable and countable. So, in fact, most languages turn out not to be decidable because there's an uncountable number of languages, but there's only a countably infinite number of Turing machines. So here's the proof, and I'm hoping this is recap. The number of Turing machines is countably infinite. Why? Well, because each one is represented by a natural number, right? It's Turing machine code. So that's how many there are. There's a first Turing machine, a second Turing machine, a third Turing machine, and so on. So the languages they accept are countably infinite. Right? There's as many as there are natural numbers. But the number of different languages is uncountably infinite. And that's a diagonalization, kind of like Cantor's proof of the non-countability of the reals. Anyway, so that's just a proof that there are far too many languages to accept via Turing machines. But it's much more interesting to find particular languages. Just saying there's a whole bunch of stuff you can't do, well, maybe we don't care about the stuff we can't do. Right? What's more important is to know, for particular languages, do we have an algorithm? Can we decide the answer to this question? Okay. So we're going to end up showing that the universal language is not decidable. Although it's recursively enumerable, it's not recursive. We can tell if a machine accepts a string, but we can't tell if it's not going to. Okay. Another problem, which is the halting problem, which I mentioned earlier, given a program, when we run it, does it halt? How many of you would have liked to solve that problem? Right? Well, who cares whether or not we can tell if a program is going to halt? Right? Gee, wouldn't you like to know whether you should reboot or you're just waiting and progress is being made? Right? So determining whether or not a program is going to halt is really a critical question in deciding, in debugging algorithms. Turing machines are just programs. Telling whether or not a machine or a program is going to halt is part of debugging. In fact, furthermore, there's another way to look at this, which is that just about every mathematical conjecture you might come up with can be rephrased in terms of, does this algorithm halt? So if we had a method, and I'll show you an example here in a moment, if we had a method of deciding whether a program would halt, we could solve just about any mathematical conjecture that's open. What? That's a really powerful statement. So let me give an example. So this is Goldbach's conjecture, which is that every even number can be expressed as a sum of two primes. Every even number greater than 2. So 4 is 2 plus 2. 6 is 3 plus 3. 8 is, what is 8? 2 primes. 5 and 3. Right? What is 10? 5 and 5. 12 is 7 and 5, right? 2 primes. That's Goldbach's conjecture, that every even number can be expressed as a sum of 2 primes. Nobody knows the answer to the question. Big open question in math. Okay. So here's an algorithm that we might write. Here's the first part of it. it's going to check whether a number is the sum of two primes. Right? So the input is n. And we just look at every pair of numbers p and q less than n. This is not the most efficient way to tell, but it is a way. For every pair of numbers less than n, check, are they prime? And do they add up to n? And if they do, then say true. But if you've tried every pair of numbers less than n and haven't found a pair that happens to be prime and whose sum is n, then you stop and you say false. This number n is a counterexample to Goldbach's conjecture. Okay? Very simple algorithm. There it is in 3 lines. Okay? So that's just checking. Here is a program that uses that as a subroutine. What it does is it just does this. It runs this little subroutine for every number n, for every even number n. So starts with n equal 4. It checks, is 4 a sum of two primes? If so, then let's look at 6. Is 6 still a sum of two primes? Yes, it is. Let's look at 8. Let's look at 10. Let's look at 12, and so on. It keeps doing that. And as long as it's finding n, even n, which is the sum of two primes, this will return true, and it will continue adding 2 to n. But if Goldbach's conjecture is false, what will happen? It will exit the while loop. It will find a number n, which, for which can't be expressed as the sum of two primes. It will halt. So deciding whether or not this program in particular is going to halt when we run it, when we just start it up. Is it going to halt? Well, that's answering Goldbach's conjecture. Yes? Yes. No. Yeah. Let me just say yes. So that's not quite a question. It's more an observation, and I'm agreeing with the observation, but there's some nuanced things I could say which would drag the class in a sideways direction, which has to do with the difference between languages that are recursive or recursively enumerable or whose complements are recursively enumerable, and I don't want to go there. Okay. But we're not talking about languages at the very moment. We're just looking at the general utility of deciding whether or not a program can halt. That's a good thing to be able to do. Because if we had a general method for doing that, we could solve Goldbach's conjecture. Okay. Here's another interesting question. So you guys, how many of you are TAs? Yeah. Really? This is why we don't have any TAs. What do you? Okay. By TA, I mean course assistant, sorry. Okay. So do you have to write Autograders ever? Here's the first assignment in somebody else's version of CS125. Write a program that prints out hello world. So here is a solution, although it's in the wrong language for CS125, but let's ignore that. Can you write me an autograder for that assignment? And what would it do? Well, you could check if it looked like this, right? Yeah, but what if the student were clever? Or what if the student copied someone else's code and put a whole bunch of blanks in there to try to confuse you? It would still print hello world. What if they got clever and they put the characters in hello world into an array, and they printed out each element of the array in turn, and still print out hello world. So the code might not look like that. Yeah. Just run their code. Okay. For how long? Yeah. Maybe they don't have the most efficient method. Maybe this program that they wrote is actually trying to trick you into solving Goldbach's conjecture. Okay. All right, so what this is going to do is it's going to run the Goldbach program. And if that halts, it will be a correct algorithm for printing hello world. And if it doesn't, then it won't. And so your autograder is solving Goldbach's conjecture. Okay. So if you have a good autograder, let me know, and we will publish a paper. Moreover, we won't just publish that paper. We'll publish a bigger paper, because it's not just Goldbach's conjecture we can put here. We can put just about any mathematical conjecture here. So let me give you a more general example. Suppose I've got a program M, and I'd like to know whether or not it's going to halt. And you have an autograder. You have an autograder for this problem, hello world. Well, what if I submit to you this? Is my program correct? Does it print out hello world? Well, it does if the program M halts. Right, so the existence of an autograder for this simple program really is the existence of a general purpose algorithm for deciding whether a program will halt. Okay? And that's a really hard problem. And in fact, there is not a general purpose algorithm that will always say yes or no to decide whether or not a purpose will halt, a general algorithm will halt. So in fact, if you come up with such a thing, the paper that we will publish will say mathematics is inconsistent. Okay, because we will have proved something that happens to be false, because there is no such thing. Okay. So that's why halting is important, right? And we're going to see how we can use these kinds of tricks in a more formal setting to prove that certain languages are not decidable, right? That certain things are impossible. And this is going to limit our ability as computer scientists to solve problems, right? It turns out that there's not much we can do. So it's surprising how well we've done. So there are two proofs that the universal language is not recursive. It's undecidable. Right? So remember, this is given an M and a W, does M accept W? We have an algorithm that can run M on W and say yes. What we're going to prove is that there isn't one which will also say no if M doesn't accept W. But just running M on W doesn't do it because it may not halt and we may not know that. So we're going to show there is no algorithm. Okay, so we're going to show two proofs. One is a slick proof, which is confusing and mind expanding, I think. And the other is a more slow, careful proof, which is perhaps also confusing and maybe not as mind expanding. Okay. We need to do a warm up. So there's a lot of paradoxes that involve self-reference. And proving these kinds of things ends up being capturing these paradoxes, in mathematics or in computer science. So consider a town where there's a barber who shaves everybody who doesn't shave himself. Seems reasonable. If you don't shave yourself, you go to the barber. He shaves you. And the barber shaves every such person. And the question is, who shaves the barber? Does he shave himself? If he does, then he shouldn't, because he only shaves people who don't shave themselves. Now, if he doesn't shave himself, he should go to the barber and get shaved, right? Because the barber is the one who shaves everyone who doesn't shave themselves. Okay, yes. The barber is a woman. Does she shave herself? Hair is androgynous. So yeah, I apologize for using, nice try. I apologize for using gender-specific pronouns, but let's do something else, which is related. So there are two kinds of words. There are what we'll call homogeneous words. These are words that describe themselves in some sense. For example, English, that's an English word. Or short, or polysyllabic, has more than one syllable. Polysyllabic, that's self-describing. Right? Then there's heterogeneous words, which are not self-describing. For example, Spanish, not a Spanish word, right? Or long, not very long. Or monosyllabic, You need more than one syllable to say that. Okay? So a word is either homogeneous or heterogeneous. And what question am I about to ask now? What kind of word is heterogeneous? Well, there's two possibilities, it would seem. Let's suppose that it falls into this category, homogeneous. That means it ought to be self-describing, right? But the definition of heterogeneous is words that are non-self-describing. Right? On the other hand, suppose it's a heterogeneous word, then it should be not self-describing. But it is, because heterogeneous, if heterogeneous is a heterogeneous word, then it is self-describing. So we can't put it here either. Okay. All right, it's annoying. Okay, so let's do this with Turing machines. So let's consider the question, given an M and a W, does M accept W? Look at that language of M's and W's, such as M accepts W. And we're going to show that there is no method for deciding yes or no. And let's assume, this is a proof by contradiction, so let's assume to the contrary that there is such a method. Let's call it the TM accept checker. And we give it an M and a W, and it checks, does M accept W? And it will say yes, M accepts W, or no, M doesn't accept W. Now, the tricky part here is that M may not accept W by getting into an infinite loop. So just running M on W is not the way that this is going to work. It's going to work by some mystical way that we're imagining, right, or that we can't imagine. We're just hypothesizing that this exists, and we will argue to a contradiction. Okay, so everyone's got the setup? Okay. So we're going to use this as a subroutine. And so here it is. We're going to use it. Give it an M and a W. Tells whether or not M accepts. So here's the thing I'm going to do. I want to sort of feed itself at some point. I'm going to get it confused. So I'm going to write a little routine that takes an input and copies it. That's pretty easy to do, right? So here I'm giving a Turing machine code as input. I'm going to copy it and give it to this checker. Right? And what does it do now? Well, it's going to run the machine I'm giving it on the input I'm giving it. So it will decide whether M accepts itself. Does it feel good? Does it accept itself? Right? As a machine, is it self-actualized? So it decides whether M accepts M, right? Which is fine, right? This is a program. It's also data. We can do that. Programs are stored as, right? Okay, good. So far, so good. Now here's the trick. So I'm going to wrap all that up into a larger program, which I'm calling Q. And what I'm going to do is it's going to take an M. It's going to copy it. It decides whether M accepts M. And then after this accept checker runs, it does the opposite. It's contrary. If it says M accepts M, Q says, nope, M doesn't accept M. But if the accept checker says M doesn't accept M, then Q says, yep. Is this clearly we can write such a program if we had this program? Right? The pieces here are trivial. Right? Copy an argument, change the answer from yes to no, or no to yes. So this program Q halts, regardless of what the input is, because this does. And what does it do? Does it accept an input M? Well, it accepts an input M if the accept checker says that M is not self-accepting. Okay? So it says yes if M, were it run on itself, would not accept. So this will accept. And if M, when run on M, doesn't accept, then Q will accept. That's the behavior of Q. Okay? Why am I doing this? To punish you, because the exam wasn't enough. Okay. So I'm going to take this box, I'm just going to reproduce it there. Okay. So just look at this for a moment if you needed to sink it in. Q takes an input M, and it's going to accept it if M wasn't self-accepting. Right. It's going to accept M. It's going to say yes if the Turing machine checker, the accept checker, says that M doesn't accept M. So then Q will say, yes, I accept you. Right. And Q given M will run M on it, well, will run M and M into the accept checker. And then if that checker says no, M doesn't accept, if it says yes, M does accept M, then Q will say no. So questions about what this does, not why it does it, but just what it does? Okay. So what am I going to now do? Yeah, I'm going to feed it to itself and watch the fireworks fly. Oh, no. Okay. Well, what happens when we feed Q itself? If we give, well, here's the behavior of Q. We give it an input, blah, and it accepts if and only if blah on blah doesn't accept. In this case, blah happens to be Q. So Q on Q will accept if and only if Q on Q doesn't accept. Q on input Q will reject if and only if Q on Q accepts. Okay, so no, right? Boom, right? So this is nonsense, and the only thing that we did, the only assumption that we made was that there's a box like this that can tell whether a machine accepts an input and tell us yes or no. That's the only assumption we made. And so from this we conclude that that assumption was wrong. There is no such accept checker, and the language LU is not recursive. Yes? The larger one reverses it gratuitously just to get this contradiction. The question is, why does this swap its answer? The answer is because it can. The answer is because a clever mathematician said, what if we did this? Oh, we get a contradiction. Oh, no. Oh, this couldn't have existed. The only purpose for doing that is to make us upset. Right? The only reason for doing this is to say, look, this couldn't have existed, because if it did, then we could have done this. I don't know why we would, but we could have. And if we did, we get a contradiction. What is the big machine? It has this behavior. A more intuitive view is, let's consider machines. So machines are either self-accepting or not. So what is the behavior of the big machine? It accepts non-self-accepting machines. That's what it's doing. So it's accepting, it's shaving non-shaving machines, right? It's accepting machines that are not self-accepting. And so it doesn't know whether it should be self-accepting or not, right? So that's, okay. All right. Okay, so this is the kind of thing that you see and you go, huh? And you go home and you look at it and you go, huh? And then maybe you go, ah, at some point. So you need to let it sink in, but it's very bizarre. Yeah? This is the barber's problem in machines. It's just coding a paradox into, does an algorithm say yes or no? Right? So that's why we did that warm-up, because it's really the same flavor. Right? Okay. Okay, so we get a contradiction, so LU is not decidable. Okay, so now we're going to do a different proof, which is a slower proof, using a different technique technique called the reduction, which will turn out to be very important when you look at NP completeness. What we're going to do first is use a diagonalization technique to show a particular language is not recursive, and then we'll do what we call a reduction. So let's see how this goes. So remember, again, that Turing machines can be viewed as numbers, right? There's a first Turing machine, a second Turing machine, a third Turing machine, and so on. And so we could actually make a table like this. Here's machine 0, here's machine 1, here's machine 2, and so on. Here are all the possible inputs, word 0, word 1, word 2, and so on. All right, so we can list all the possible inputs, maybe epsilon, then 0, then 1, then 0, 0, then 0, 1, then 1, 0, then 1, 1, then 0, 0, 0, then 0, right? Just list every possible word input up here, every possible machine here. A given language you can find by reading across. So this machine accepts the first 2 words, not the next 2, yes, the next 3, not the next 2, and so on. The machine that accepts nothing, well, look, it's right up there. It just says no. Right? It just halts and says no. Right? So every recursively enumerable language, every language for which there's a Turing machine appears as a row in this big table. It's an infinite table, right? But if there is a Turing machine, it's on this table. It corresponds to a row, and its language is spelled out for us. Right? So Turing machine that accepts primes, it's going to say no, no, yes, no, no, oops, yes, no, whatever. Okay. I'm assuming that the encoding now was in decimal, but it was. Okay. Good. So those are all the Turing machines. The rows are the languages. And I want you to focus your attention on the diagonal. No, no, yes, yes. No, no. No, no, yes, yes, no, no. No, no, yes, yes, no, no. And now I'm going to flip them all, just for fun. Yes, yes, no, no, yes, yes, and so on. So I'm creating, well, I'm just changing all these. And now this is a language, right? Because in each column, I'm saying whether or not, the red box is saying, should I accept this word? Is this word in the language? Yes. Yes, this word is in the language that this red diagonal is defining. No, W2 is not in the language. No, W3 is not. Yes, W4 is in the language that I am defining. So this diagonal, which has flipped the answers, flipped all the diagonal elements, that defines a language. Okay? And I'm going to call that language LD, the diagonal language. And it's exactly those words, I, that are not accepted by the machine with the same number. Words that are not in the language of M, words I, WI, such that WI is not in the language of MI. Okay? That's the diagonal language. The questions about the diagonal language of the definition. Right, you give me the 53rd word. Is it in the diagonal language? It depends whether or not the 53rd machine doesn't accept it. If the 53rd machine doesn't accept it, then it is in the diagonal language. Okay. That's the diagonal language. And now we claim that the diagonal language is not accepted by any Turing machine. And the reason is, we kind of made it do something different than all of these Turing machines. Yeah? These are all the Turing machines, period. Yes, every possible Turing machine is listed. We're creating a new language that isn't accepted by any of them. I'm sorry? That's right. Yes, that's exactly what this slide is going to do. It says, why isn't LD not recursively enumerable, even? Well, if it was, it would have to be accepted by some Turing machine, MK, right? The kth one on that list. But LD, by definition, contains WK if and only if the language of MK doesn't. That's the definition of LD. So LD differs on machine K on word K. It does exactly the opposite. And it's not equal to the language of MK for any K, so it's not accepted by any Turing machine. It's not even recursively enumerable. Okay, so it's a sort of contrary language. No Turing machine can accept it. Okay. All right. Good. All right, so here's where we're headed. We've shown that the universal language is not decidable, right? Is not recursive. And we've shown that LD is not even recursively enumerable. We've got two problems that are hard, right? So think of these as Goldbach conjecture problems. We don't know the answer. But here we actually know that they're not decidable. Goldbach we're still up in the air about. But here are two languages that we know we do not have algorithms for. What we're going to do is we're going to do what we did with Goldbach's algorithm. We're going to slip it in to other programs and show we can't decide things about those programs, because if we could, we would be deciding things about LD and LU. Okay? So that same trick we did with Goldbach's conjecture, right, where we showed that you can't write an autograder, because if you could, well, look at this program that sneakily tries to solve Goldbach's conjecture first, and then you get to autograde it. So we're going to do the same thing, but instead of Goldbach's conjecture, we're going to use these two languages, LD and LU, for which we've already proven are not recursive. Okay, and here's the general technique. It's called reduction. And the question is, how could we use an algorithm for one problem to solve another one? So let's consider the case we've got a problem of type X. Right? We'd like to solve problem X. So there's an input to X, and we'd like to say yes or no, depending on whether we should. And let's suppose we don't actually have a method for solving X. What we have is a method for solving Y. And Y accepts an input of type Y. And the Y solver tells us, yes, this is a good Y input, or no, it's a bad Y input, right? Yes, it accepts, or no, it doesn't. Well, a reduction looks something like this, where we take an input of type X, and we do something to it, and make it look like a problem for the algorithm Y. Give it to the algorithm for Y, and Y gives us an answer, and we just use that. And if we're clever, that will tell us whether or not X should have been accepted. And that's a way we can solve X, if we can do something like this. So if we have a decision algorithm for Y, we can use it to decide the X problem if we can do something like that correctly. That make sense? Right. So for example, suppose you have a method of telling whether or not a number is negative. I can trick you into telling me whether or not a number X is greater than a number Y. How would I do that? Well, I would give you X minus Y. You would tell me whether or not it was negative. From that, I would know whether or not X was greater than Y. Right? So I can use your algorithm to solve my problem by doing something ahead of time. And the nice thing is that if I have an algorithm for deciding Y, if I can do Y, then I can do X. But there's a flip side of this. If I already know that there is no algorithm for X, then we know that Y can't exist. So this is the way we're going to parlay our knowledge that LD and LU are not decidable, show other languages are not decidable. We're going to show that if Y were decidable, we could decide X. But we know X isn't decidable, so Y couldn't have been. Okay, so that's where we're going. So here's the first reduction, and it looks like this. And it's a reduction. I'm not sure I like this one. Chandra wanted me to put this in. I'm going to blame it on him. Hold on a moment. I can't do it. I get the sense this is going to confuse you, so I'm going to apologize to him instead. Okay. Now he's going to watch this tape and go, what on earth was Lenny doing? Hold on a moment. Okay. Okay, I shouldn't show you my internal demons, you know, like this. All right, yeah. No. All right. So using a trick like that, we can show the universal language is not decidable. Okay. We've already shown it's not decidable by that slick, you know, contrary proof. So let's see how we can show other languages are not decidable using these reductions that we just talked about. So here's a problem which we mentioned earlier. Given an algorithm, does it halt? We saw how important that is, right? I mean, it's debugging a program, solving gold box conjecture, solving any other conjecture in mathematics. So we're going to show how if we had a decider for whether or not a program would halt, we could create a decider for the universal language. Okay? And we know there isn't one. We know there isn't one because we've already proved that. Okay? So this is what it looks like. Well, the first question is, what are the input and output of the reduction? So assume we had a decider for this halting question. So this is expecting what as input? It tells whether or not a program halts. So it's expecting some program as input, some Turing machine description. And we would like to create a decider for the universal language. What do inputs to the universal language look like? A machine and a word, right? And we'd like to know whether that machine accepts that word. So we have to come up with a technique for giving this box, a machine and a word, and outputting, the reduction is going to output some machine description, and then we're going to give that to the halting decider. And what we would like to be true is that if the halting decider says, yes, M prime halts when run on blank input, then in fact, M would have accepted W. And if it says no, M prime does not halt when run on blank input, then in fact, M would not have accepted W. So this is the way, if we can do this, if we can create an M prime from M and W, we can use this box to decide the universal language, which we know is not decidable. Does that make any sense, or are you fatigued at this point? Fatigued. This is where it's going to get cool, though. All right. Okay. Brain stretch. Arm stretch. Don't poke anyone's eye out. Okay. I'm going to ask you to think this much more. This is a time for a supreme effort. Okay. So supreme effort, think this much more, and we're going to get there. All right. So here's the idea. We want to show that deciding whether or not a program will halt can't be done. We want to show it can't be done. We don't know that. We want to show that. But we do know that deciding whether or not a machine accepts an input, whether a program accepts an input, we know we can't do that. We've already proven that. So we want to show that you can't tell halting, and we only know that you can't tell if a program accepts a given input. And these two are very related questions. So we just want to show that relationship. And what we're going to do is we're going to make an assumption that, in fact, we could tell whether or not a program will halt. And here's that box that we're assuming exists. It says whether or not a program halts when given no input. When we just run it, does it halt? Assume this exists, and we're going to build this thing which we know cannot exist, which is the decider for the universal language. That's what we're doing. So the input to this decider for the universal language is a program and a string, and we'd like to know, does the program accept the string? And we want to use this halting decider, and we're going to give it a different program. I don't know how it relates to M and W. We're going to give it a program, and we're going to ask it, does this program halt? And if it does, we'd like its answer to be exactly yes and no, when, depending on whether or not M accepts W. If we can do that, then we've done a reduction. So here is the program, and let's look at it for a moment. This program M prime has M and W as constants. They're just big constant strings. And what it does when we run it is it runs M on W and halts if M accepts W. If M doesn't accept W, M prime just, it may halt. I'm sorry, it doesn't halt. It may get into an infinite loop. It may observe M halt on W or not and say I reject. But M prime will not halt under that condition. So M prime will halt only if M accepts W. So do you think you could write this code given a program and a string? The answer is yes. All you're doing is calling that program on that string. And if it stops and says yes, then you halt. Otherwise, you just loop forever. That's what M prime is. Okay? So I guess the question is, how do we know whether or not M halts and accepts? And the answer is that the reduction doesn't do that. The reduction just creates this program. It creates this code given M and W. Okay? Creates that code. And now let's see what happens. Okay, that's what we just had a moment ago. So this decider says yes under what condition? Only if M prime halts no input, right? That's how it's been constructed. So this big box will say yes exactly when this machine halts and accepts. But when does this machine halt and accept? Only when M accepts W. Okay, so this machine, this decider is saying yes only if, or if and only if M halts on blank input, which is the case if and only if M accepts W, which is to say if and only if MW is in the universal language. So it's really deciding whether or not a machine accepts a string. So what we've done is we've taken this halt decider and we've built a decider for the universal language. Okay. Let me do something which has a more specific language in it, because this gets so abstract because we're hypothesizing a machine that takes another machine as input, which was created by a machine, which took a machine and some data as input, right? And so there's so many levels of abstraction here. It's okay to be confused. I'm going to make one thing more concrete. So we're going to show that you actually can't decide much of anything about programs. So for example, given a program, does it accept the set of palindromes? Given a program, does it correctly print out hello world? Given a program, does it meet the specification? Given a program, well, we just saw it, does it halt? Right? So all of these questions are not decidable. And we have no method of solving any of these fundamental questions about program behavior, which is why debugging is hard. Right? So in fact, take a look at this, L non-empty. Given a program, does it do something other than nothing? Does it accept anything at all? So I was a teaching assistant at some point, and I was for an introductory class. And there was an exam, and I had to grade some handwritten code. And the student had written this big mess. And this wasn't my forte. And I looked at this thing for a while, trying to figure out what was this big block of code doing and how was it affecting the variables that had already been declared and manipulated. And then after a long time, it dawned on me, and I handed it to Jim, who was much quicker than I. And I said, Jim, what does this code do? This block right here. And he looks at it for a moment, and he says, nothing. It didn't do anything. The whole thing was a no-op, but it was a no-op in a complicated way that was hard to tell. So I couldn't tell, my own personal experience with undecidability of questions like, does this code do nothing? I couldn't tell whether this bit of code did nothing, right? And now I feel okay about it because there's no algorithm to do that. There's no algorithm to tell whether a piece of program is crap or whether it's solving the world's problems. Okay. So let's take a look at this one last question. So I've got a program. Suppose I assign you the problem, create a Turing machine that accepts only the string 0 to the 374. I want you to accept that string and nothing else. And I want you to hand in a Turing machine description that does that. Okay? And I'd like to auto-grade your programs to see whether or not you've correctly coded an algorithm that accepts this language. Okay? So I'd like to see whether, could I do that? Could I come up with an autograder for that? That's the question we're investigating. And let's assume that I could do that. Okay? And what I'm going to do is I'm going to show that if I could do that, if I had an autograder for this question, then in fact we could decide, again, the universal language, and we know that's not possible. And this is the way we're going to do it. So I want to show how I can tell with my autograder that M, whether or not M accepts W. I can tell whether or not a given machine accepts a given string. And I'm going to do it by turning this into a program that I will give to my autograder. Right? What I'm going to do is I'm going to take an M and a W, and I'd like to create a possible solution to this homework problem with a property that if it really does, if it's a correct algorithm for the homework problem, if this is its language, then in fact M would have accepted W. Right? So I want to write code that does that. And here's what I would do. So you give me a machine M and a machine W. And you'd like to know, does M accept W? You'd like to decide, the universal language, right? And this is what I'm going to do. Given an M and a W, I'm going to write this program that may or may not solve the homework specification. So I'm going to create this Turing machine right here, this blue box, that might accept 0 to the 374, and it might not. And I'll do it in a way that if it does, if it is a correct algorithm for the homework problem, then M will accept W and otherwise not. So in other words, whether or not it's correct is going to depend on whether or not M accepts W. So let's ask the question, what is the language of this M prime? So take a look at it. It depends on M and W. So what is the language accepted here? It depends, right? Depends on whether or not M accepts W. So suppose M does accept W. What is the language then? Suppose M accepts W. What is the language of this algorithm? What does this algorithm do? Right, so if M accepts W, it won't accept any string that's not 0 to the 374, but it will accept 0 to the 374, so that's the language. So this algorithm, if M happens to accept W, will be a correct solution to this problem. Right? And if M doesn't accept W, what is the language of this machine? What does M prime accept if M doesn't accept W? Nothing. Nothing. Okay, so again, here's the whole picture together. You give me in M, so here's our algorithm for checking the homework, whether or not I have correctly created a Turing machine or a program that accepts the language 0 to 374. Now you give me an M and a W. I build this. I build this program out of M and W, and I give it to this autograder. And we already know that the language of this machine is exactly 0 to 374 if and only if M accepts W, right, by our construction. So this code that I've given to this checker for whether or not a language is equal to 0 to 374 is deciding whether or not M accepts W. So I've tricked the autograder. I've tricked the decider for whether or not a language of a machine is just 0 to 374 into deciding whether or not a machine accepts a given word. And from that we conclude that this box doesn't exist because this whole system collectively decides whether or not M accepts W. Okay. I should stop there because you need 2 minutes to go, oh my God, I can't believe you put us through that, and then go. So are there any questions before? Okay. Go home and look at the stuff because I know the beginning stuff is really cool. The later stuff is just the same but a little bit more formal. That's all that's going on is we're slipping one program into another and making it do things it wasn't intended to do and showing that it can't do things because we could trick it into doing impossible things.